Learning mathematics is very, very difficult to many people, second only to learning how to speak English. Do you have difficulty? Don't be embarrassed. It's a lot of people don't know what they're doing when they get up there and do their mathematics. We're going to introduce you today to Fort Bend Tutoring, honey. Personalized math tutoring is the solution.
Hello ladies and gentlemen, this is Mr. Witt with Fort Bend Tutoring, and today's tutorial is going to be about rational functions, finding the vertical asymptote. That's what we're going to be focusing on today. So first and foremost, you should be aware that when you're dealing with a rational function, it's because you have an equation in the form of f of x, or the variable y, equal to a function divided by another function, where that function in the denominator, this q of x right here, it can't equal to 0. And why can't it equal to 0? Because it would be undefined. That's why. You can never have 0 in the denominator of a fraction, which in essence is a rational function. Just saying. So, because a rational function is a fraction, many of the rules that apply to fractions also apply to rational functions. Alright, let's go over a few things about finding the vertical asymptote. Alright, how to find vertical asymptotes. The first thing you want to do is you want to take your rational function and factor it completely. From there, if it's a reducible rational function, meaning that you can simplify it, go ahead and do so. So you want to factor it completely, you want to simplify, and then you want to set any remaining factors equal to 0 that you find in the denominator. Alright, so any remaining factors in the denominator, you want to set them equal to 0 and solve. The equations that you get from that will be the vertical asymptotes. Alright, so those are the steps that we'll be doing in our examples here. Alright, let's check it out. In problem number 1, we have f of x equals -2 divided by x minus 3. So in each of these examples, I'll be showing you the factored form of the original equation. Well, this original function, this f of x equals -2 divided by x minus 3 it's already in its simplest form. You can't factor this. So we'll be moving on to our next step, and that is any remaining factors, you want to set those equal to 0 and solve for x. So in order to find my vertical asymptote here, I'll set the denominator, this x minus 3, I'm going to set it equal to 0, and then I'm going to solve for my variable x. So that means I'll be using the addition property of equality here and adding 3 to both sides of my equal sign so I can solve for my variable x. You know? So I'm bringing down x. And it equals to 3. And what you see before you is the format of a vertical line. Every vertical line will always be in the format of x equals to a number. But this particular line is your vertical asymptote. And speaking of asymptotes, vertical asymptote is going to be a vertical line where our function will get closer and closer to it as it moves away from 0. So the next thing is, when you're presenting your answer, in other words, your vertical asymptote, you need to show the entire equation. It's not just a number 3, it's the entire equation, because this equation is the actual vertical line that the function will be getting closer to, but never touching. Alright, so let's go ahead and graph it. Alright, so notice that I have the original equation here, the f of x equals -2 divided by x minus 3. We just found that our vertical asymptote is x equals 3, and in order to graph that on our Cartesian plane right here, we'll be showing this as a dashed or dotted line. I prefer dashes. I just prefer dashes. I don't know why I prefer dashes, but I do. So you can go ahead with your little dotted line. I'm going to be doing dashes, okay? So I'm looking at 3 right here on the x-axis, and I'm going to have a vertical line, a dashed vertical line going right through that. All right, I know yours is straighter than mine, but there we go. That's it. So never use a solid line when representing your vertical asymptote, and you should always graph your asymptotes first. It really helps define the areas that you'll need to graph the actual function in. And that's it. That's number 1. We just graphed the vertical asymptote for our function f of x. All right, there we go. Let's move on to problem number 2. In problem 2, we have y equals x squared plus 1 divided by x squared plus 2x minus 3. The factored form of this equation is going to be y equals x squared plus 1 divided by x plus 3 times x minus 1. Now, what I did in the denominator, we had a quadratic trinomial, and I factored it, all right? So if you need to brush up on factoring quadratic trinomials, you want to check out this video right here. Check that out. I'm in it, explaining things. So what we'll do from here is we'll see if we can simplify this equation. Now, we already factored it, but is it reducible, all right? So can we cancel out any factors here? No, we can't. So therefore, we'll be setting both factors in the denominator equal to 0 in order to solve for our vertical asymptotes. All right, so here I go. I'll have the equations x plus 3 equal to 0 as well as x minus 1 equals 0. And I'm going to solve for x in both. So in the first equation, I'm subtracting 3 to both sides. All right, and these additive inverses will cancel, so I end up with x equals -3 for that first vertical asymptote. Next, I'll be solving for the second equation, so I'll be adding 1 to both sides of the equal sign here, and x equals to +1. And it's these two equations, x equals to -3 and x equals to 1, that is your vertical asymptotes. I'm going to red box this. That's right, gift wrapping my answers for my teacher. There you go. Making things a little bit more organized. Yeah, not messy like you. All right, so then we're going to go ahead and turn the page. So turning the page, we're going to graph now. That's right. Notice that I have my original function here, but you know, we ended up with two vertical asymptotes. Our vertical asymptotes were x equals to -3 as well as x equals 1. These are our vertical asymptotes for this rational function. And now we'll be graphing them. So remember, each of these equations will be a vertical line, and you will always use a dashed or dotted line to represent those vertical asymptotes. So at -3 on the x-axis, I'll have a dashed line going right through here. That's right. That's it. And then, let's put it in view. All right, it's being a little stingy there. We'll go ahead and graph our vertical line x equals 1. Sure will. Look at that. Just beautiful. Just lovely. That's right. So these are going to be our vertical asymptotes graphed. Once again, I strongly suggest that you graph all of your asymptotes prior to graphing the rest of your rational function, as it defines the regions where your rational function will lie. It just makes things simpler. At least it does for me. All right, and this is going to be the graph for your vertical asymptotes, just like that. And now we're moving on to the next problem. Okie dokie. In our next example, we have g of x equals 7 divided by the quantity of x plus 2 squared. This function is already factored, but I could expand it. All right, let's say that I expand it. All right, I'm going to expand this. Let's say that I expand the denominator to show the factors raised to the first power. All right, how about that? Okay, there you go. So I'm showing here that I recognize that this factor, this linear factor, x plus 2, is actually being squared. That's what we had in the original problem. So in order to find our vertical asymptotes, we actually have the factors repeated. This x plus 2 factor is repeated. So you can just rewrite it as x plus 2 equals 0, x plus 2 equal to 0. Now, of course, I'm going to the extreme here, but I'm just making a point that you end up with the exact same equation, that the process remains the same. However, your equations that you'll get from this will be the exact same. All right, so you'll end up with an equation that reads x equals -2, and you'll end up with a twin, identical twin. That's right, not fraternal. Identical twin that looks exactly the same. All right, so that being the case, you can ignore 1. In other words, since it's repeated here, the multiplicity is more than 1, you only need 1. Okay, so you only need 1. So all you need is x equals -2 in this case. All right, you only need to represent the vertical asymptote once, and even if you didn't, it would overlap. So there you go. All you need is this, x equals to -2. Done. You end up with 1 vertical asymptote is the point. All right, so I'm red boxing it. There you go. And just to be clear, I'm not eliminating the second equation because it's wrong or irrelevant. I'm eliminating it because it's redundant. You're repeating the same answer and it's not necessary. So therefore, you're going to use just the one x equals to -2. And that's it. Done and done. Let's graph it. All right. Alrighty now, check this out. Okay, we have our original function g of x equals 7 divided by the quantity of x plus 2 squared. We just found that our only vertical asymptote in this equation is x equals negative 2. That's it. Just the one vertical asymptote, and we're going to graph it. So I have a vertical line. I got a vertical line coming up at negative 2, going through negative 2 on our x-axis here. And I'll be using a dashed line. That's right. Dashed line, just like that. All right, I know you like your little dotted line, but mine's going to be dashed, just like that. That's the graph. On to our next problem. All right, in problem number 4, that's cuatro in Espanol, we have h of x equals 2x divided by x squared plus x. I want to rewrite this in its factored form. You always want to start out by completely factoring your original rational function. So I have h of x equals 2x divided by our GCF, the greatest common factor in the denominator is x. If you need to brush up on that, check out this video right here on factoring the greatest common factor. Okay? We'll be able to factor out an x. That'll leave us with x plus 1. Notice that in the numerator and in the denominator, we have an x. That means we can actually simplify this. So if I simplify this, I can cancel out the x's there. And you should. Our focus here is finding the vertical asymptotes. Anytime you have a reducible rational function and you can eliminate a factor, do so, because that factor will not be a vertical asymptote. In fact, it will produce a hole in your rational function. So make sure you check out our video on finding holes in rational functions. All right? So the simplified form of our rational function here is going to be 2 divided by x plus 1. Just like that. So we'll be setting our remaining factor in the denominator equal to 0 to solve for our vertical asymptote. That means I'll be setting x plus 1 equal to 0 and then solving for the variable x. So once again, what happened? We factored our original function completely by factoring out the GCF of x in the denominator. Those x's canceled out when we simplified it, and any remaining factors in the denominator is what you're going to set equal to 0 to find your vertical asymptote. All right, so here we are, right back at the present. We're subtracting 1 to both sides of the equal sign. I had additive inverses that canceled out on the left side of my equal sign. I brought down my variable x, the equal sign, and 0 minus 1 is negative 1. That's my vertical asymptote. I have a red box coming. I just boxed this thing up right here. You were there, you're a witness. On the witness stand, Mr. Witt, he boxed it up. He boxed up that answer. So this is our vertical asymptote. It is. You're excited. I'm happy for you. And now we're going to graph this. Let's move on. So I have my original function here. Remember that original function? You were there. You know it. You recognize it. It's h of x equals 2x divided by x squared plus x. I want to say that again. H of x equals 2x divided by x squared plus x. I think the second time sounded better. The vertical asymptote that we just found was x equals negative 1, and I'll be graphing this. I don't like that 1. Neither do you. Let's fix it. This is an ugly one. It really is. I think I can do better. All right. Is that negative 1 good, or do you like it when you make a 1 like this? Which do you prefer? I think now this looks better. Is the base too long down here? Okay, I'm getting sidetracked. Anyway, the vertical asymptote is what we want to graph now, and it's going to be x equals negative 1. Remember, the format for every vertical line is always x equals to a number. In this case, we have x equals negative 1. Negative 1 is the value that we should be focusing on. Let's go ahead and look at our Cartesian plane, aka our rectangular coordinate system, and graph it. Oh yeah, it's coming. So we have x equals negative 1. Let's go ahead and put a dashed line through this negative 1 over here. There you go. I know you're jealous. Don't be jelly, because my graph looks better than yours. All right, there you go. There you go. What you say? Oh, yours is better than mine? Forget you then. I ain't scared of you no more. So here we have x equals negative 1, and there's my graph. It's done now. That was problem number 4. Let's move on. All right. problem number 5, ladies and gentlemen. That's right. We have f of x equals 2x squared plus 2x minus 12 divided by 3x minus 6. We want to factor our original function completely. So that means I have f of x equals, we can factor out a GCF of 2 in the original numerator, right? So factoring out 2 here, that leaves me with x squared plus x minus 6. All of this is going to be over. In the denominator, I can factor out a 3, right? We'll factor out a 3, and that leaves me with x minus 2. Okay? And now, notice that we have a quadratic trinomial in the numerator that can be factored. So, continuing to factor here, I'll end up with x plus 3 times x minus 2. All of this is going to be over 3 times x minus 2. All right? Notice in this problem, our x minus 2's will cancel out. That's right. X minus 2 divided by x minus 2 is going to be 1. So it cancels to 1. In other words, we can simplify it, reduce it, and end up with the following problem. 2 times x plus 3 divided by 3. Or 2/3 times the quantity of x plus 3. Either way would be correct. The bottom line is we no longer have a factor in the denominator that contains our variable x. No, we just have the number 3. That's it. That's it. What does this mean to you? This means that you're not going to have a vertical asymptote. No. And you're asking, well, what happened to that x minus 2 in the denominator? That will become a hole in this graph. It'll be a hole. Yep, a hole. So as far as the vertical asymptote is concerned for this problem, you're going to put this answer right here. You're going to say none. You don't have any vertical asymptotes in this equation. Nope, not for this rational function. I'm going to put a red box around this, because this is the answer. You don't have one. Because you ended up with a reducible rational function, in other words, we were able to factor it out, we were able to simplify this, and we were able to eliminate every factor in the denominator that contained our variable x. Because we no longer have any factors with the variable x within it, we don't have a vertical asymptote. We don't. We need to have a factor with the variable x in the denominator in order to set it equal to 0 to find a vertical asymptote. If you cannot do that, you will not have a vertical asymptote for that function. That's right. In this case, we'll have a hole. All right, that is problem number 5. All right, so we have our original function here, that f of x equals 2x squared plus 2x minus 12 divided by 3x minus 6, and we found out that we don't have a vertical asymptote. Remember? It's none. We don't have a vertical asymptote in this problem, therefore we don't have anything to graph as far as the vertical asymptote is concerned. All right, and now on to problem number 6. All right, in problem number 6, we have f of x equals x plus 2 divided by x squared minus x minus 6. The first thing we want to do is we want to try to factor this rational function completely. So I'm rewriting this as f of x equals x plus 2 divided by x minus 3 times x plus 2. All right. Once again, we run into a reducible rational function. In other words, we can simplify this. So when I simplify this, I end up canceling out this x plus 2. But remember, when you cancel when everything is multiplying and dividing, it doesn't cancel to 0. Oh no, it cancels to 1. So we were left with a 1 in the numerator there. So this becomes 1 divided by x minus 3. But notice we still have a factor in the denominator that contains our variable x. So this factor, that's what we'll be setting equal to 0. So do it. All right, go ahead and get to it. We'll have the x minus 3 equal to 0, and then solving for this, we end up with a vertical asymptote that is x equals 3. You're fantastic. You just understood everything I just said. You're amazing. From now on, I want you watching every video that Forbidden Tutoring makes. Just saying, because you understand. Go ahead and wrap your answer up in a nice box. Don't let it escape. Contain it. That's right, because it's dangerous. Answers are dangerous. So now I'm going to graph this. Okay, so let's go ahead and graph that up. On to our graph. Notice that I have the original function. F of x equals x plus 2 divided by x squared minus x minus 6. And we found that our vertical asymptote is x equals 3. All right, and I'm going to graph this with a dashed line. Here it is. So, starting at 3, you look at that. Look at that. I'm at 3 on the x-axis. I'm going to put a vertical line, a dashed vertical line right through that area there. There you go. There you go. And done. This is the graph of my vertical asymptote. There you go. All right, and now on to our final problem, number 7. So in problem number 7, we have f of x equals 2x divided by x squared plus 2x minus 8. The first thing you want to do is factor your function completely. So we'll have this rewritten as f of x equals 2x divided by x plus 4 times x minus 2. That's it. There you go. Notice that none of our factors will cancel out. In other words, this is an irreducible rational function. Irreducible. You can't simplify it any further. You can't reduce it. So we'll be going ahead and setting both of these factors here in the denominator equal to 0 in order to find our vertical asymptotes. So we'll have x plus 4 equal to 0 as well as x minus 2 equal to 0. And you'll be solving for x in each of the equations. So that means I'll be subtracting 4 in the first equation to end up with x equals negative 4. In the second equation, I'm adding 2 to both sides of the equation to end up with x equals to 2. And these two equations are your vertical asymptotes for problem number 7. I'm going to be red boxing this now. Red boxing it. That's right. Done and done. Let's go ahead and graph these. Alright, so we have our original function, f of x equals 2x divided by x squared plus 2x minus 8. We found our two vertical asymptotes to be x equals negative 4 as well as x equals positive 2. Graphing our vertical asymptotes on our Cartesian plane here, you'll end up with the following graph. We'll have a dashed line going through negative 4 on the x-axis, a vertical line just like this, just like that. All right, and then I also have x equals 2. Yep, just like that. Vertical line right there. Okay, and this is the graph of your vertical asymptotes. Now, for those of you that want to gain a little bit more knowledge, check this out. Notice that we have two vertical asymptotes. And when it comes to vertical asymptotes, your rational functions will never touch the vertical asymptotes. With horizontal and slant asymptotes, your function can actually go through those on occasion. And what I want to show you before I wrap the video up is what happens between the two vertical asymptotes in most cases. So let's check it out. This is what can happen between vertical asymptotes. You can have, in most cases, either a parabola. So notice that these dashed lines here represent my two vertical asymptotes, and between them, no matter what happens on either side of those, I could have a parabola right in between that. It could be a parabola that goes up, or I can have a parabola that goes down, as I'm showing here. In addition to that, you can also have what looks like a cubic function between the vertical asymptotes. So it could look like this between the two vertical asymptotes, and it could also look like the reverse of that, like this between the two asymptotes. So these are common graphs that can occur between vertical asymptotes. All right, so just to make you aware, to enhance your graphs when it comes to rational functions. All right, and this, ladies and gentlemen, concludes our video on finding vertical asymptotes in rational functions. As always, please like, comment, and subscribe to our YouTube channel, Fort Bend Tutoring. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Witt, and Fort Bend Tutoring. Peace.
We certainly hope you enjoyed today's presentation by Fort Bend Tutoring. Did you understand the program? Would you like to rate us or give us some feedback or subscribe to us? Leave a nice comment. Don't just leave something ignorant on there. If you didn't understand the lesson, ask the professor to explain it for you. Don't just get mad and write something ignorant on there.